This is our second video on non-uniform circular motion. Here we've got a pendulum bob of mass m swinging from a rope of length L. At the instant depicted, we also know both the angle theta the rope makes with the vertical and the mass's speed. Let's derive expressions for the centripetal acceleration, the tangential acceleration, and the rope's tension. As we have come to expect, we're probably going to have to draw a free body diagram here. So let's do that. mg goes straight down, and then the rope has a tension, goes up kind of like that. There we go. And if I want to draw that theta in, if that's theta in the given diagram, then I believe this angle right here would also be theta. We've said now, when we're talking about circular motion, that our coordinate axes need to be in line with accelerations. And if something is curving, you ready for this? It is definitely accelerating toward the center. Therefore, that has to be one of the axes. And the other axis then has to be at right angles to that. I'm going to put a double asterisk by that. That's really important right there. Usually we call the axes x and y. You know what? I'm going off grid here. I'm going to say that that's the centripetal axis, and this is the tangential. How's that? You don't like it? I don't care. Okay. Well, what do we do here? Centripetal acceleration. Well, let's see. Centripetal acceleration, what's the equation for that? Isn't it v squared over r? We know those. We know v, and we know the radius of curvature. It's the length of the rope. Okay, well, that was easy. All right, how about the tangential acceleration? Probably this is going to be a little bit more work, but if we're going to find the tangential acceleration, we need to use Newton's second law in the tangential direction here. Look at tension is not in the tangential direction at all. The only force component that is in the tangential direction is mg sine theta. We write Newton's second law here, F net is equal to ma. In the tangential direction, mg sine theta. That's the only one. And that's equal to the mass of the object times the tangential acceleration. The m's cancel. So the tangential acceleration is going to be g sine theta. All right. What else are we asked to find? We're asked to find the tension in the rope. To find the tension in the rope, you can see we're going to have to write a Newton's second law equation. And it's going to have to go in the centripetal direction. Let's do that. Let's sum the forces in the centripetal direction, what I've called the centripetal direction. In that direction, we have tension and we have mg cosine theta. You might be tempted to say that they're equal to each other. Tension and mg cosine theta are equal to each other, but that is not the case, is it? This mass is accelerating towards the center. Therefore, the tension has to be greater than mg cosine theta, and that has to equal the mass of the object times the centripetal acceleration, which we already said was v squared over L. So I think the tension is going to be, if I factor out an m, v squared over L plus g cosine theta. All right, so far so good. Whenever we know the two perpendicular components of any quantity, we can always find the magnitude of the overall or total or resultant vector using the Pythagorean theorem. For part C, what would the expression for A total look like? What we would have to do is we would have to use the Pythagorean theorem on these two accelerations. We'd square that, add them up, and take the square root. I don't know, can I do that? Can I keep those both on the screen? All right, we'll see what we can do here. So the expression for A total, and we're not going to simplify it, but A total would be the centripetal acceleration squared. So that would be basically v to the fourth over L squared, plus, I'm just going to go g sine theta, whole thing squared, square rooted. That's what it would look like. If we know the components, we can use the Pythagorean theorem. Letter F, let's finish this video by saying if we now wanted to find the bob's speed at a later instant, see, we only have the speed at this particular one, but let's say we wanted to find the bob's speed at a later instant, why would we want to use conservation of energy instead of kinematics equations 1 through 4? Maybe conservation of energy would be a better choice. Why would it be better for sure than kinematics equations 1 through 4? It might not be the perfect choice because there might be some frictional losses or something, but it's definitely going to be better than kinematics equations 1 through 4 because the equations only apply whenever the acceleration is constant. And you can see here that the acceleration is definitely not constant. Sine theta, theta is always changing, v is always changing. So the acceleration here is not constant. Those kinematics equations, don't use them.